Hey there, y'all. Hey, Beethoven got a side gig. He works for Amazon. He's an Amazon Prime deliverer, so you might see him driving a truck in your neighborhood soon. So he may not be with me all the time. So welcome back to chemistry. It's good to see you. We're going to learn about measurements today. That's what we're going to be talking about today is measurements. All right. So as we go through this together, it's going to sound a little picky. Okay. And um, the thing with measurements in chemistry is it matters. The amount that you're able to report, and particularly the uncertainty, really does matter. It does matter a lot. So, what I want us to be able to think about, particularly in chemistry, is that how precise and how accurate you can be does matter in chemistry. So we've talked about some Mars exploration that recently just happened. The first set of those was in the early 2000s when they sent Spirit, a Mars Explorer rover, and it recorded measurements and sent back data every single day. All right. So what they were striving for is to get the most accurate information as possible and precise information. And we'll talk about each of those. But you sent a rover all the way to Mars, land on Mars, the miracle of science that was, and all the engineers and thousands of people, and probably hundreds of thousands of labor hours, and millions, if not billions, of dollars to get that rover there. You want it to be able to take accurate information, not kind of guessing, but, but in really precise information. So that data, all that energy that was used to get it to Mars, we want to get the best kind of data you can. So your data is only as good as your measuring tool. Okay, so let's talk about that. So how do measurements relate to science? So a measurement is a quantity that both has a number, okay, in a unit. If it doesn't have a unit, it doesn't mean anything. Okay, so it can't just be 5, it has to be 5 meters. It can't just be 82, it has to be 82 milliliters. Okay, so it has to have a number, some sort of number, and a unit. Okay, so they're the fundamentals of all experimental sciences, which is what physics and chemistry and biology are that you've taken here at school. So for that, it needs to be important that these are correct as they can be, okay, to get them as correct as possible. Okay, so we've talked about this before, but the way that scientists represent data is in scientific notation because chemists deal with very large numbers, something to the 10 to the 11th, meaning that this is a very large number. This number right here that represents this galaxy is a very large number. So that means this exponent, when you use scientific notation, is that there are 11 zeros after the number 2. So you've used this before. And certainly you've done it in classes with me. If you had me before, you've also done it in math class. So make sure you understand scientific notation and how to move the decimal point. So you can express a really large number, not having kind of put it in your pocket. It's like taking a very large number and putting it in a backpack. You put all your books in a backpack in the school. This is what scientific notation does. It allows you to understand very large numbers or very small numbers. So we're going to talk about the difference today between accuracy, precision, and error. Sometimes accuracy and precision in our everyday language is they're almost used like they mean the same thing. They're similes to one another, but they're actually different. Accuracy is the measurement of how close you are to the actual value of what is measured. Okay, so how close are you to what it really is? How close are when you measure something with a ruler or you measure the amount of volume of a liquid in a beaker? How close to you to the real measurement? And precision is how close you can repeat that measurement. Okay, so you can oftentimes it's thought of this way: the accuracy of a measurement is compared to a correct or accepted value, and precision is how many times you can get that value again. So this is the best way I think to understand it. And throwing darts, the goal, the accepted value is the bullseye, that little red area right here. And accuracy means I've hit the bullseye. I've hit what I'm looking for each time. Precision is that I'm consistently hitting the bullseye. So if I hit the bullseye once, I was accurate. If I hit it 3 times in a row, I'm accurate and I'm precise, so I can repeat my ability. You can repeat your results. Okay. Now this one right here, you have poor accuracy because if you're aiming for the bullseye here, you're a little bit off. Okay, so you have poor accuracy. You're not hitting the target that you want, but you are having a cluster of darts around there. So you have good precision. You're repeatable. Okay, but you have poor accuracy, right? Poor accuracy and poor precision means you're all over the place. You got a dart on this side, a dart over here, a dart over there, and then you're neither are you hitting the targets or are you getting them close together. So this is what we talk about. Accuracy is getting the actual value that is desired or compared to a standard or corrected value, and precision is to be able to do that over and over. Yes, that's the difference. So an accepted value is a correct value based on reliable references. Okay, so these might be constants. We'll talk about constants a lot. We'll talk about Avogadro's number. We'll talk about what a mole is. We'll talk about those types of things that are accepted values that you compare things to. An experimental value is something that is derived from a laboratory experiment and may be updated. Okay, it may be updated. All right, so the difference between the experimental result that you find and the accepted is called error. How close are you to the accepted value when you do your experiment? How close are you? And that difference is a percentage called percent error. Okay, so what you do is you take the experimental value that you received, you compare it and you subtract the accepted value and you make that a percentage. So you have your error, what you have, divided by the accepted value would be your percent error. So error is found by taking what you got in your lab, subtracting it from what's accepted. You take the absolute value, which means it's always a positive integer, okay? And you divide that by the accepted value, and that is your percent error. Okay, so for instance, if the accepted value for the boiling point of water is 100 degrees right here, and you notice your thermometer reads at 99.1 degrees. So you take your experimental value, subtract it by 100, the accepted value, divided by the accepted value, okay? And you make that into a percentage. So that means you have a 0.9% error, okay? Your error is 0.9%. Or in other ways, you're 90% correct that way as well. Okay, so the accepted value for boiling point of water is 100. The accepted value for the freezing point of water is 0 degrees Celsius. So that's when we talk about those accepted values. Okay. So just because measuring a device works doesn't mean you can't assume it's accurate. So you think about scales. The scale below has not been properly what's called zeroed or calibrated. So for instance, you can kind of see that the little dial here was starting around, about 7 pounds. Okay, so when this person stands on this scale, it's not going to be accurate. It's not going to read their actual weight. It's going to read it 7 pounds heavier than they really are. So this has to be calibrated. So this has an error built into the actual device. It's inaccurate. Okay. So what we have to do is we have to report in the right significant figures. Okay. So significant figures is a significant thing in chemistry, and sometimes it feels like, here's what I can compare it to. It's like grammar. When you write for your English or your history teacher, or even you write for me, when you write lab reports, you have to have proper grammar and punctuation and subject verb agreement, those sort of things. And so significant figures is like the pickiness of a grammar, and it matters if you want to communicate properly. All right, so let's talk about this. Suppose you estimate the weight that is between 2.4 and 2.5 pounds to be 2.46 pounds. All right, the first two digits, the 2 and the 4, are known. You know those. You know that because you know it's either between 2.4 and 2.5. So you know these digits, but the last digit is estimated and involves some uncertainty. Okay, all three digits contain useful information. However, they're called significant figures. So significant figures in a measurement are all digits that are known, okay, plus the last digit was estimated. Okay, so these are the digits we know, okay, that we can rely on based on our scale. So for instance, going back to our scale, we can read down to probably a half a pound. If we squatted down and looked at the scale, okay, you could read down at least to the pound, maybe estimate to the half a pound on that scale. Okay, so measurements are always reported in the correct number of sig figs. That's a shorthand for it, is sig figs, because calculations depend on the numbers of significant figures. Okay, so here's some rules. Okay, your book has these, that insignificant figures, all non-zero digits, any number that's not a zero is significant. So if it's a 7, an 8, a 1, a 4, a 6, a 2, an 8, a 9, 3, those non-zero numbers are always significant. Okay, so something like 24.7, 7.743, 714, all of those are significant. Okay, zeros are where to get you into a little bit of, you have to think a little bit. So zeros that are in between non-zero numbers. So the zeros in 7,003, the zeros that are sandwiched between the 7 and the 3 are significant. This zero that's between the 4 and the 7 is significant. The zero right here between the 5 and the 3 is significant. So all of these have 4 significant figures. That zero counts. The next one, the leftmost zeros, these left ones, they call them leading zeros. It's another one. They are not significant. Okay, so this one right here, 0.00099, only has 2 significant figures. 0.0071 only has 2 significant figures, and the same with 0.42. So to write these in proper significant figures, you have to use scientific notation. So that's where that comes in. So 0.00099 is going to be written in 2 significant figures as 9.9 times 10 to the minus 5. Okay, because you moved the decimal point 5 places. Same thing with 0.0071. You move the decimal point 3 places to make it 2 significant figures. Okay, and then the last one, the zeros at the end of the number, of if there's a decimal point, if the decimal point is actually written or typed out, it's significant. So 43.00, so it's to the right of the decimal point, those are significant. Okay, 1.010, these 2 zeros are significant. And 9.000 meters is significant. So all 3 of these sets of numbers have 4 significant figures. Okay. All right, and the last ones, zeros at the rightmost end of the decimal of the numbers are not significant. Okay, if there's no decimal point, they are not significant. Okay, they're not significant. Right. So we'll let's go into a couple examples here. Sometimes it's easier just to go through some examples. All right, so we can measure, we can have a one significant figure here because we're going to estimate this 1 meter. How far is this piece of wood, or what is the length of this piece of wood? We could estimate it to about 0.6. It's a little over half. So we could imagine it might go to 0.6 meters. If we divide that meter stick into some 10 sections here, into centimeter sections, so these are 10 centimeter sections here. We can now estimate, oh, that's probably, we can add a digit because we have more information. So this is going to be 0.61. We can add that extra digit because of our instrument that we're using. So if you further divide that down, okay, into even smaller sections, into centimeter sections here, you can now add another digit. So it's not only 6.6, it's 0.6. It's not only 0.61 like it was up here. Now it's somewhere between 0.6 and 0.61. So it's 0.607. Okay, so based on the ability of your instrument, the accuracy and precision that your instrument is using. Obviously, with this instrument, you can't be as precise. It'd be hard to reproduce this one because you're estimating more. Here, you're able to be more precise. You can repeat this over and over again. Okay, so we're going to do some lessons together. We won't cover this in the video now, but during class, we'll go over some of the rules and apply those significant things. So that's it for this lesson to kind of warm you up. and I'll see you in class soon.